Morning, everyone. Let's start. It's 10 a.m. Welcome to today's 2COOL2WASTE cluster webinar, The Future of Energy Efficiency, Practical Solutions for Heat Recovery and Electrification. My name is Sofiane Barry. I am from GAC Group, and I represent the Terminator project. It is a pleasure to be your host today for the next 2 hours. Thank you all for joining us today. I can see participants joining from all across Europe and beyond, so a warm welcome to everyone. Before we get into the content, just a quick word on the context for today's session. This webinar is part of the framework of the European Sustainable Energy Week 2026. For those who are not familiar, it is the largest event in Europe dedicated to clean, secure, and efficient energy. It is organized by the European Commission's Directorate General for Energy, together with CINEA, the European Climate, Infrastructure, and Environment Executive Agency. This year is actually a special one. It is celebrating its 20th anniversary. The main policy conference took place in Brussels and online from the 9th to the 11th of June 2026. And the theme was a clean, secure, and competitive energy union. And throughout the rest of June, the conference is followed by a whole series of sustainable energy days and cluster webinars across Europe, and that's exactly the kind of sessions that we are running today. It's a great framework for projects like ours to connect with the wider clean energy community and share practical results. So, what is the 2COOL2WASTE initiative? 2COOL2WASTE is a cluster of sister EU-funded projects all working together on heating and cooling solutions to decarbonize the European Union process industry. 16 projects are part of this initiative, and together they are tackling industrial and district energy needs, thermal energy management, heat reuse, and industrial decarbonization. The common goal across all projects is simple: lower emissions, greater energy efficiency across Europe. Today, we are bringing several of these projects together in one session to share concrete, real-world applications to heat recovery and electrification. Let me quickly walk you through today's agenda. We'll start right now with a short Mentimeter icebreaker, just 5 minutes, to get to know who is in the room. Then from 10:10 to 10:45, we'll have our first panel, Cooling Without Wasting Energy, Can Heat Help Us Cool, with speakers Katia Klinard from Terminator and Uli Jacob from Rewich, moderated by my colleague Carla Bourne. From 10:45 to 11:20, our second panel, Heat Pumps Turning Low Temperature Heat into Useful Energy, with Veshak Somasundaram from Geocene, Matteo Saclamente Lozano from SUS Heat, and Michael Strubble from ExquiHeat, moderated by Uli Jacob. Then from 11:20 to 11:55, I will personally moderate our third and final panel, Energy Systems Working Together, Buildings, Grids, and Flexibility, with Rongling Li from the SEEDS project and Claudia Vanucchi from the Synergy Nets project. And finally, we will wrap up and close the session from 11:55 to noon. You can see the full list of today's speakers on the screen now. We have experts joining us from Terminator, Rewich, Geocene, SUS Heat, SEEDS, Synergy Nets, and ExquiHeat. A really strong lineup, and I will introduce our speakers' panels in a bit more detail later. Before we jump in, a few just housekeeping rules so that we have a smooth session. Please first stay muted unless you're invited to speak. This just helps us avoid background noise. Second, please use the chat. If you have any questions or thoughts at any point during the session, feel free to drop them there. We'll be keeping an eye on it throughout. Third, if you'd like to speak directly, you can use the raise hand feature and we'll bring you in. Fourth, please note that this session is being recorded and cameras are entirely optional. Feel free to turn yours on if you'd like. We'd love to see your faces, but there is no pressure. And finally, we are a global, inclusive community here today, so let's keep the discussion respectful, kind, and constructive. All right, so before we dive into the panels, let's hear from you. We have a quick Mentimeter icebreaker to kick things off. So you can now see a QR code on your screen. Please take a moment to scan it with your phone. It will take you directly to our Mentimeter poll.
Could you please
Sofiane, can you put up the QR code again?
Yeah, of course. Sorry. Here it is. Okay, so we can see that we have a lot of participants coming from the research and academic background. Also some consultants, 2 students, 1 industry representative, 1 technology provider. Maybe we'll have other responses. Let's move to the second question. Which country are you joining from? I have participants from Germany, Poland, Ireland, France, and also outside Europe. I see Indonesia here, the Philippines. So participants from Belgium, Austria, Italy, the UK, Slovenia, Denmark, Sweden, Italy, Hungary. So we have many different countries here represented, which is very good. Let's move on to the third question. In 1 or 2 words, what does energy efficiency mean to you? So mainly sustainability, effective use. There is no planet B. Yeah, absolutely relevant. Help the networks, low carbon emissions, more output, less input. Challenge, zero net carbon. Very good. Let's move on to the fourth question. Which topic are you most excited to explore today? So we have flexibility, heat recovery, cooling from waste heat recovery, decarbonization. Yes, it is absolutely topics that we're going to cover today. Cooling as well. Very good. And let's move on to the last question. What is one question you hope this webinar will help you answer? How to reduce entropy gen? How can we use flexibility? Absolutely. How to achieve net zero? How to stop global warming? I'm sorry?
Oh, sorry, it was my phone by mistake. Sorry, I'm just listening.
No problem. No worries. Thank you. Thank you to all of you for providing very insightful answers. Let's keep some of these questions in mind as we move through the panels today, and we'll try to answer them. All right, so let's move. Let's move on to our first panel, and I will now hand over to Carla Bourne, who will moderate our first panel. Please, Carla, the floor is yours.
Thank you, Sofiane. Good morning, everyone. I'm Carla Bourne, and I'll be moderating our first panel of the day, Cooling Without Wasting Energy, Can Heat Help Us Cool? This might sound a little counterintuitive at first, using heat to produce cooling, but it's actually one of the most promising avenues for industrial decarbonization today. A huge amount of energy in industry is consumed by cooling and refrigeration processes, often powered by electricity. At the same time, an enormous amount of waste heat and renewable heat goes untapped every day. The question this panel will explore is how can we use that heat instead of wasting it to actually produce the cooling that industry needs. To explore this with us, I'm joined by two speakers. First, let me introduce Dr. Kadja Klinar. Kadja is an assistant professor and researcher at the Faculty of Mechanical Engineering in the University of Ljubljana, where she's part of the Laboratory for Refrigeration and District Energy. Her research focuses on heat and mass transfer, caloric refrigeration, and thermal switching technologies. Kadja represents the Terminator project today, a Horizon Europe project developing a groundbreaking energy conversion technology. Welcome, Kadja. And alongside her, Dr. Yuli Jacob. Yuli is the managing director of Dr. Jacob Energy Research, an international consultancy specializing in renewable energy and energy efficiency with a particular focus on solar cooling, thermally driven cooling, and industrial waste heat use. He's also senior scientist at the University of Innsbruck, and Yuli represents the REWICH project today, a Horizon Europe project bringing together over 25 partners from across Europe to develop and demonstrate innovative absorption and absorption cooling technologies driven by a mix of industrial waste heat and renewable solar thermal energy. Welcome, Yuli. Let's start with our first guiding question for today. How can advanced cooling and conversion technologies manage hot surfaces and turn part of their heat into electricity? Let's go ahead.
Should I start?
Yes, you can.
Okay. First of all, thank you very much for invitation to this webinar. I will try to briefly present what we are doing in the Terminator project. But of course, if somebody is interested more, you can contact me yeah, I can provide more details. So what we are doing in Terminator project is heat to power conversion. So we are trying to convert, let's say, waste or excess heat to energy. And I'm sure that you know already different technologies. The most, let's say, popular is thermoelectric energy conversion. So thermoelectric energy conversion is one of the technologies that can convert waste or excess heat into electricity, but it's not the only one. So there are also other technologies like organic Rankine cycle, and organic Rankine cycle is also already used in industry to convert excess or waste heat in industrial processes to electricity. And these two technologies are already, let's say, present on the market and are, let's say, conventional. But in the Terminator project, we are dealing with two technologies that are not yet so common or not yet so represented in the market. And these are thermoacoustics and pyroelectrics. Just to briefly explain what these two technologies are. So thermoacoustic technology is about transforming acoustic energy into heat and vice versa. So this technology can be used for either having refrigerators or heat pumps or generation of electricity, because acoustic energy can be transferred in mechanical motion or acoustic waves can be generated because of temperature difference. So having hot heat source and heat sink can produce acoustic oscillations, acoustic waves, and this can be then used, can be transformed in mechanical energy and by this also in electricity. And pyroelectric technology, we have solid state materials that exhibit pyroelectric effect. And this effect is basically the change in polarization of the material. And this change in some materials is temperature dependent. So if we subject this material to heat sink and heat source, so to heat it up and cool it down periodically, this generated charge can be then used in electric circuit via some resistor or some component. And by inducing voltage, we can have electric current, and by this we have electric power. And in this project, we are trying to combine these two technologies. Both technologies operate in, let's say, similar way. They both need regenerator. And in this regenerator, the idea is that we couple these two effects and get more compared to having only one technology. The regenerator itself is a porous structure of these special materials. And through this porous structure, heat transfer fluid oscillates and transfers heat between the heat sink and heat source and also this regenerator. So the idea of this project is to get as much electricity out of the device that combines both technologies as possible. But because this is a very basic research project, at the end of the project, the TRL of this device will be between 3 and 4, meaning that we will basically prove the concept and test in laboratory. But of course, the idea is to provide application that is quite clear. And this is also why we already have 2 project partners that are covering different applications. One application is photovoltaics, and the other application is district energy. Even though we are trying to generate electricity, at the same time we use heat. So consequently, we are actually cooling the source. And the idea with photovoltaics is that our device can be put on the photovoltaics, and by cooling it produces also another part of electricity that can be that can be either directly used or stored. And with district energy, the idea is that our device can produce enough electricity to power sensors that are mounted on the pipes and that are mounted on such locations where there is no, let's say, accessible electricity otherwise. The idea is to provide, let's say, up to 1 watt power, and the idea is to use this heat from, let's say, flat surfaces, which is the case for photovoltaics, and curved surfaces, which is the case from the district energy pipes. So our device will probably at the end look something like the figure shows. The idea is that it is very thin and flexible to some extent. And basically, the heat input provides electricity outputs. I know that it's a lot of information that I provided, but I hope that it's at least a bit clear what we are doing. But yeah, of course, we can discuss further.
Yes, thank you, Kaja. Perhaps, Yuli, do you have any additional information for this question? There is also the second question that you can also work on, which is for a reminder, why is necessary to exploit waste heat and renewable heats to generate cold?
Yeah, thanks, Carla. First of all, for the introduction. Maybe I should just give a statement on the first question, because we have a different project. So we are not using heat to convert this heat to power ideas, which were presented by Katja before. So we are more looking into to use the waste heat from thermal processes in industry, but also from renewables to produce cold. So the second question at the end of this panel, but maybe Katja want to add something also from her side again to the second question, because I think she already said something on that, and then I would like to follow up with our project.
Okay, then I will, thank you. I will just briefly respond to the question in the chat. So about how much electricity can be generated from this technology and with what efficiency. The idea of using electrocaloric or pyroelectric materials is that the energy efficiency of this solid state phase change is higher than phase change between, let's say, liquid and vapor states. So if we check the efficiency of the process itself in solid state, it's more reversible than in other phase transitions. But there are other problems related to the material processing. So this limit is theoretical and is not yet achieved. So currently, it's difficult to say if this technology has higher energy efficiency compared to other technologies like thermoelectrics or organic Rankine cycle, because we cannot directly compare. They are not on the same scale yet. But the potential for this is higher. But we need to first prove it experimentally. Otherwise, it's not. It doesn't help even if the efficiency is 100% if we cannot reach it. And the amount of electricity provided is in the scale of watt, because the technology is still at early stage. There are some guidelines how this can be scaled up, but it will not be scaled up to such extent that as, for example, organic Rankine cycle or thermoelectrics, because the niche of these two technologies is more low power. So let's say maximum to a few watt. Thank you.
So, all right, I think with that I can take over. There are no more other questions in the chat as far as I see, going into the presentation from Katja before. So yeah, thanks for all for the short introduction already, Carla, about our project, the REACH project. So now we are looking more in a different direction, using waste heat and also heat from renewables to be converted through thermally driven chillers, heat pumps, to provide cold for different kind of processes in the industry. So REACH is a project with 26 partners, as you already said, with 4 pilot installations in the food and beverage sector, 2 of them. Another one is in the paper industry, and the 4th one is in the fuel production from biomass. And with that, we have some quite nice projects, pilots, where we try to use the waste heat from different purposes to convert it into cold, which is then used again in the different processes on site. And therefore, we're using different kind of technologies, different kind of innovations, and especially on thermally driven chillers, absorption and adsorption chillers, really to enhance the overall efficiency of the systems and to decarbonize then these kind of industries here in the sectors which I've briefly explained before. So it's one side the waste heat on different levels. It's also about to use different streams there. And on the other side, it's also to look into the use of renewables, especially in industry, how to use heat from solar. So it's not about PV, it's about solar thermal installations. So to use heat from different kind of collectors. In that case, it's about a high vacuum flat plate collector, which allows you to provide temperature to levels above 100 degrees Celsius, which is then easily be used in the different processes also in industry. So we're using and consuming waste heat and renewable heat to run this kind of chillers. You have to know these chillers which are implemented in these 4 pilot installations are not the common ones which you can buy from your traditional HVAC companies. Those are especially designed and also implemented then and monitored in the project based on new developments from the partners within the project, from the scientific side, so from the researchers. So there are some new innovations here, especially about hybrid chillers, which are a combination of compressor chillers and thermally driven chillers to use both sides, both potential energy efficiency increasing sites. So at the end, to have a high EER, energy efficiency ratio of such chillers, especially if you have high ambient temperatures, which is usually for compressor chillers also somehow difficult to reach their top efficiency. And if you combine this and have such hybrid chillers, then you use both sides and both advantages of both kind of technologies. That's the first approach. The second one is that we have also some new developments that those kind of chillers provide not only one chilled water temperature, but also 2 with one machine at the end. So especially in industry, we usually do not have only one temperature level, which has to be supplied to the different processes. There are several ones. And it's the first time of kind here that such a chiller now provides from a same black box different temperature levels, which are not mixed by bypasses in the piping, but we have 2 kind of evaporators, so some internal heat exchangers, which allow you to extract 2 kind of temperature levels here for this purpose on this demo site. And with that, there are a lot of innovations which are part of the project. And coming back to your question, how to elaborate to use waste heat. So this is really the core here in the project. And if you probably go to the second slide, then I will dive in some more into this question and to try to also push the discussions later on here. So starting especially in industry, it's important to do first of all the analysis of the different heat streams and also the cooling demand, and try to figure out what are the operational schedules and the patterns to bring that together, and first to all to do some pinch analysis. And with this information, with this data, then you can start to elaborate what kind of system, including thermal energy storage, could be the correct design. And this is most important, especially such implementations in existing systems is really truly different if you probably can design a system from the scratch. So if a new facility, a new factory will build, then it's much easier than as you have to go to existing site and just first of all to figure out how to do the implementation and to get to the right system. So that's also part of the project. So we have digital twins, which allows us also to do this kind of simulation firsthand before the real implementation happens. And that's also something which is, I think, quite important for the future, for the decarbonization of the industry, to use all kind of technologies, tools to make it much more easier. And last thing, which is also belonging to the question of the panel. You should also have a close look on the existing infrastructure, what you can already use there, and how the integration really would look like at the end. So what are the integration paths to do this kind of implementation, especially of novel technologies belonging to thermally driven chillers, also these kind of renewables, because that's something which usually is not used in industry in their common standards, in their processes to do some baking of cookies, or also to produce beer in the breweries. So it's really to help all the companies and the installers and the engineers which are somehow linked to the projects, what they really should do, and how to do this correct design at the end. So that's what the project is about. And with that also somehow on the question, I hope to get already some insight. Of course, if someone is interested, you can have a look on the project website and find more information what the different technologies could provide to you, but also how the implementation paths maybe helps you also for real projects. And so with that, I just want to end this short wrap-up on the ReWitch project, and I think I'm quite open for discussion along with Katja about the other project here in this panel.
We still have a few minutes before the Q&A starting. Do you have any reaction, Katja, about what was being said? Or if not, we can. Now. Yeah, okay, sure. So thank you both. This has been a quite impressive and fascinating discussion. Let's now open it to the audience. So please use the chat or the raise hand feature if you have a question for Katja or Yuli. I'm just looking at the chat right now, and there is a question for Yuli saying, can we get more than 2 cooling temperatures from the same chiller, and how this is controlled with material or some other control strategy? Moreover, what materials are listed to be used in such chillers?
Yeah, thanks for that question. I try to answer it in a short way, because there we can start a discussion for several hours now. Yeah, first of all, this chiller, as I said before, has two kind of heat exchangers on the evaporator side, which allows you, as it's a water lithium bromide chiller, so it's a standard chiller which is enhanced with a second evaporator to provide temperature levels, first of all, at about 5 degrees Celsius, and the other level which is necessary at that point is only 15 to 20. And with that, you have a much more higher efficiency, COP of the overall machine. So those are the two temperature levels here on this kind of chiller, which is provided to the system in Greece. And the control, of course, that's also an issue. But the point is, as I said, there are two heat exchangers, so we have two inlet and outlets which are separated, so the control of it is also separated to the two processes independently, as we have no mixing valves or something like that, as we have two kind of heat exchangers here in this machine. So from the control side, this is for the temperature levels, that's not an issue. But of course, for the overall system and alongside with the implementation for the with the different heat sources, which is waste heat and also the renewables, there's a new control system which is then implemented, and also the strategy behind developed by the different partners in the project. If you are interested in that, of course, you can contact them or just send me an email, and then I will forward this to the colleagues which are doing this kind of work. Related to the materials, as said, it's a lithium bromide water chiller, absorption chiller. So we have only water as a refrigerant and lithium bromide as an absorbent. There's nothing else in the machine itself. So we have only those kind of two materials, and with that, so it's not a problem from this side. As said, it's more a kind of engineering, how at which point you use this kind of solution and refrigerant inside the machine to provide these two temperature levels in the two kind of heat exchangers.
Thank you for that response. That was very complete. I see that Martin, you have a question. Please go ahead.
Hi, my name is Morten Björk, Swedish serial entrepreneur, delivered more than 1,000 turnkey projects in 40 plus countries on 5 continents, among which I delivered 5 gigawatt of district heating in China, balancing wind farms to the grid, utilizing peak valley pier for competing out coal-fired district heating, utilizing high voltage electrode boilers. I also work with waste heat recovery, also thermal systems in collaboration also with Turbodan regarding ORC from Italy before. So currently I'm involved in developing solar concentrators, dual tracking systems, where we can do, that is like a wind, mesh type wind transparent, where we're currently experimenting both with hot water, pressurized hot water, but also thermal oil. So in this case, we also experiment with smaller absorption chillers within cooling. So there are several such projects available where we can organize funding, also via European Union. So it will be interesting to see if we can, from this group, form to do such pilots and applications together, especially with you, Mr. Uli Jacob, as we have such projects and funding available to do this type of experiments already. We have industrial plants, several previously delivered to several areas. So it will be interesting if we can take this further, if you can contact me, and see if we can integrate this into mutual finance plan with the European Union innovation funding, but also with project financing, as we already have existing plans to connect to that limits the installation cost. So it will be interesting if you have, as also the previous question maker speak, to see if you have some references that we can compare with, to see how we can implement together, as we are currently also using a Ukrainian technology within solar concentrators that is currently financed by Swedish Energy Agency to test even in Sweden. So it'll be very interesting to connect with you and see how we can do this further. So if you have an engineering team, please contact me and we can see if we can combine our teams and take the discussion further.
Yeah, thanks for this input from your side. For sure, we can help here in different directions. So happy to make the contact. As there's another question here in the chat, which is somehow belonging also to your comments and questions about are these projects somehow visible? Yes, of course. There will be also some public site visits organized in the near future, and there will be also a lot of videos available, video material. So as I said, implementation will take place this year. So we'll start in after the summer break, and with that there's also a lot of monitoring data available. You can find a lot of information also on monitoring data already from the chillers itself on Cernedo. So Cernedo is the platform from the European Commission where you have to put all this data which is public available in a place which allows you to easily download it. So you can also find a link directly on the REWITCH website. First of all, secondly, that there are more projects from other cluster members here, which are not part of this webinar today. So if you have a look on the other projects, you will find also some more projects funded by the Commission so far in this purpose, also in the direction of using solar heat from concentrator collector technologies. And so there's a lot of information available which probably helps you for your future developments, and happy to take the contact further in the next few days.
So maybe I appreciate that. So maybe the organizer of this meeting can connect us in the meeting to each other so we can take it further, right?
Yeah, sure. I can put my email address here easily in the chat, but it's the organizer who should decide how to exactly go ahead with that.
Exactly. Thank you.
Yeah, welcome.
Thank you, Martin, for that question. The time is passing, but we still have a bit of time for 2 more questions. Joachim is asking in the chat for Terminator, what would you say is the main challenge, collecting heat or converting it?
Yeah, it's a very good question. So both are challenges from our point of view. So we are engineers and we are more focused on the device itself, not on the material itself, because the groups of material scientists produce the materials and they try to make them as good as possible. And in Terminator project, we bought material and we are trying to get as much out of it as possible. So the challenge we are working on is how to collect heat and how to transfer heat to this material. So in the pyroelectric case, we use ceramics, and in thermoacoustics, it's stainless steel porous regenerator. So we are focusing more on heat transfer point of view, trying to optimize the channels, the convective heat flux. We are trying to reduce pressure drops in the devices and all these details that affect heat transfer part of the device. And of course, we also try to optimize the electronics part as much as possible, but the limit is still the material. And yeah, we choose the best material that is available on the market. But of course, there are researchers in material science that try to improve the materials. So yeah, this is what we are doing in the Terminator project.
Thank you. And lastly, we have two questions from Bokuki, which are, where could we see this machine? I think it was related to the chairs. And will the recording and the presentation will be available afterwards. And also, please feel free to contact the speakers if you have more questions afterwards. So where could we see the cheaters? That was the question. I think it was for the Rewitch project.
Yeah, as I said before, you can have a look already on the website. I already put the link here in the chat. So there will be the material available, including the information on which sites you can find which kind of machine. So the implementation will take place after the summer break, as I said. And with that, all the information, including photos, videos, and so on, will be presented quite soon.
Great, thank you. Thank you so much, Kaja and Yuli, for such discussion on how heat rather than electricity can power the cooling industry needs, and for sharing such concrete examples from Terminator and Rewitch. That brings us to the end of the first panel. I will now hand back our second panel, heat pumps turning low temperature heat into useful energy, moderated by Yuli. Jacob. Thank you.
Yeah, thanks, Carla, for the first panel, and thanks, Katja, for your participation together with me there. So I want to start with the second panel now of this webinar today. It's now about heat pumps. Have a look into how to use low temperature levels and heat to use it as a useful energy again for different purposes. Here in the second panel, we also have some initial questions which should be answered by our three speakers, which I will present in the next few minutes. So it's all about how we can use geothermal heat at the end and how we can use industrial waste heat and to use it for the different purposes in industry to meet the different heating demands. maybe including also some thermal energy storages and some renewables. So those are the two questions which the three speakers also should try to answer within their presentations of the three different projects. So with that, I just want to introduce the three speakers of this second panel. So with us today, we have three projects. So first of all is Vashika from the University of Southern Denmark. He's their postdoctoral researcher and PhD in mechanical engineering. He's educated from India. He will present the project on geothermal heat used for in heat pumps at the end. And with the second speaker, it's Matteo from Royal Institute of Technology. He's a PhD candidate in energy technology, and he has a master's degree in chemical engineering from Polimi in Italia. And our third speaker is Michael Strobel from Dr. Jacob Energy Research. He's also a PhD candidate from the University of Innsbruck. He's there looking into technical engineering, and he has a master's degree in energy and environmental engineering from Leipzig University of Applied Science. And he's representing the Exquisite project. Matteo is presenting the SAS Heat project. And all of them are looking into heat pumps from a different perspective, starting from geothermal into the use of waste heat in industry and to enhance the different kind of systems. And with that, hand over to the first speaker and allow you to present the project and probably also already answer one or two of the questions which we have shown before in the slide before for this panel, which then should allow us to start a discussion later on.
Thank you, Julia, for the introduction. So I am Vaishak Somasundaram. I am a postdoc fellow from University of Southern Denmark. I work on a European Horizon project, which is having an objective of developing a high temperature heat pump for the industrial application. So this high temperature heat pump, as you all know, this is one of the most promising solution for decarbonization and electrification of industrial heating processes, especially up to temperatures of 200 degrees centigrade. And if we see the energy demand up to this temperature, that is 200 degrees centigrade, it accounts for about 35 to 40% in Europe. And in that itself, up to 100 degrees centigrade, if we see, it accounts for around 10 to 12%. So when it comes to heat pump, when we are upgrading the heat, the temperature of the source as well as the sink at which we need to deliver it really matters. So what we are focusing here is that we are trying to upgrade low to medium temperature geothermal heat to meet temperatures in the range of 180 to 200 degrees centigrade. And Geocene is a Horizon, European Horizon project, which specifically focuses on this. And for this particular application, we are using water as the refrigerant, because for applications where the sink temperature is above, we can say 160 degrees centigrade, water is the best refrigerant for that particular temperature ranges, and its performance increases with the rise in condensing temperature. For this, you can see on the screen the schematic of the heat pump, which is being developed under this project. And this heat pump, the source of this heat pump is a geothermal steam, which is coming from coming at a temperature of temperature in the range of 125 to 140 degrees centigrade. If you see this temperature, 120 to 140 degrees centigrade, it is slightly low to medium geothermal temperature, we can say. And in Europe, this temperature can be found, we can found this temperature in countries such as Italy, Turkey, then Hungary, some parts of Germany, at a depth of almost 2000 meters. Now, for our project, we are targeting, or our main source is a geothermal plant which is located in Italy, Tuscany region. And we have monitored the temperature of that geothermal well, and based on that, we have developed this heat pump. So the well temperature is 120 degrees centigrade, and we are upgrading it to 200 degrees centigrade. So this temperature is essential for different process industries which are related to food and beverages, textiles, paper and pulp industry, chemical, as well as industries related to leather, rubber, plastic and glass product industry. Even though all the process in this industry doesn't require this temperature, some processes which requires the temperature in the range of 180 to 200 degrees centigrade are the distillation process, drying, certain kind of pasteurization. So these processes are being met by boilers, central boiler, which produces steam at a very high temperature and pressure, and this is throttled for different applications. So the heat pump which we are developing here, the idea is to replace this central boiler, not for a specific process. And one more thing I would like to add here is that the working cycle of our heat pump is a vapor compression system. So there is a phase change involved in that. So this heat pump is specifically suited for applications which is involving steam generation or water to steam conversion. And if you see the configuration, we could see that there we are having a different stages of compression. This we came with this configuration because of the properties of water, because water is having very high discharge temperature, so that it should not exceed the operating temperature of the materials which are used to develop the compressor. So in order to maintain the operating temperature well within the capabilities of the material, we have come up with this particular configuration which is having 4 stages of this compression. So that is just a brief regarding the how we can upgrade geothermal energy into different or for different process heating application. So we could take discussions further from here.
Yeah, thanks for this short introduction so far of the project. There's already just one question in the chat, which probably helps also to move on the discussion later on. The question is, what is the cooling and capacity of the heat pump, which is now presented with this 4 kind of compression here in this project?
Yes. So the prototype which we are developing, it is designed not based on the cooling capacity. It is based on the heating capacity. It is about 50 kilowatt. But when you ask the cooling capacity, it is around some 45 kilowatt, I remember. And here one point which is related to what the question is being asked, because of the intercooling which is present between the each stages of compression, some amount of the heat which is added by the compressor is removed in the intercooler. So that heat which is removed in the intercooler, presently it is not being used in the system.
So as far as understood, it's because the question is again about cooling and heating capacity. So which means we have a cooling capacity of 40 and 50 on heating side for the prototype, right?
Yes.
Okay.
Yes.
So just to clarify it, because then the colleague there should get the answer with that. All right. Yeah, thanks. Sounds good. All right. Yeah, as you already answered one of the questions raised here in this panel, I just want to hand over to the second speaker. So Matteo, maybe you can give us an insight of the SAS Heat project, which allows us then later on to start a discussion with all the different attendees here in the webinar.
Yes, thank you, Uli, for the introduction. I hope you can hear me well. So similar
yes, to
okay, good. Similar to my previous colleague in Geoscience project, in SUS Heat, we are also using a high temperature heat pump for upgrading ambient or waste heat in factories around 200 to 250 degrees for process heat. Yeah, so basically has the mentioned before, right now, many factories, they still use gas boilers or coal boilers to produce the heat that they need. And this heat is used in different energy vectors, as steam, hot oil, or even hot air. And what we want to do with the high temperature heat pumps is to electrify and therefore decarbonize process heat. So the concept that SUSHEAT proposes is that we can take the waste heat that is currently being not used or curtailed in the factories. We can recover this waste heat and upgrade it through the high temperature heat pump that in our case, we are using a stirring machine, a stirring heat pump using helium as a refrigerant. We don't have any phase change within the heat pump because it's only compression and expansion of the helium. So we can recover through a heat exchanger heat from the waste heat through the helium and then upgrade it to higher temperature level, around 200 to 250, and deliver to the process at the temperature that is required, right? And also in our concept, we have two thermal energy storage tanks, one at lower temperature, so around 75 degrees, and one at higher temperatures, around 220 degrees. This is in order to address, sometimes we have mismatch between the heat demand and the heat availability. So when you have, for example, when you have waste heat, but you don't have any demand, you can store this waste heat in the low temperature tank, low temperature test tank. At the same time, if you don't need steam, but you have low electricity prices, so it's cheap to operate the heat pump, you can charge your high temperature thermal energy storage in order to discharge it when the electricity prices are very high. So we are optimizing also the economic performance of the whole system by producing heat at lower cost. So yeah, in our project, we are working with an industrial partner that currently they have the heat pump operating around 150, 160, even 180. And with the SUSHEAT project, we want to extend the upper temperature level to 200 and 250 degrees to demonstrate the technology of the heat pump and the thermal energy storage up to a TRL level 5. And the concept also includes concentrating solar power, in this case, Fresnel linear collectors that can work in parallel or in series with the heat pump to provide the process heat to the factory that is required. Normally, we are targeting the application for this project is between food, paper, chemical, and pharma industries, where the steam level is not so high. So, for example, in North Europe, that the electricity is cheap, but we don't have a lot of solar irradiation. The heat pump with the test tanks makes more sense. In South Europe, where you have let's say, a higher solar resource, a smaller heat pump with a Fresnel collector can be adapted to provide the same power. So we are working on developing the technologies, doing the techno-economics of the system, and yeah, we are building a validation plant at KTH. So hopefully by the second semester, we can do the commissioning of the experimental plant. And yeah, if you have any question, also I think in the future, if you want to visit us at KTH, you can contact us and you can come and see the plant operating. And yeah, if you have any question, please feel free to ask.
Yeah, thanks, Matteo, first of all, for this short insight of the SAS heat project with all the different aspects on the heat pumps, thermal energy storage, but also on the Fresnel collectors, as far as understood, so the concentrating collectors. So as we had already a discussion question beforehand on this kind of technology, maybe that's something which can discuss be more in depth in the Q&A session here later on. I do not see directly here a question related to your presentation now. Maybe there are more for the discussion later on. So I think with that we try to get some more insight on the third project, and with that we will then open the discussion among all participants. So thanks first of all, Matteo, to you. With that I introduce and invite our third speaker to give an insight about the Exquisite project. So Michael, it's your time.
Yes, thank you very much, Uli, for the introduction. Yeah, my name is Michael, Senior Project Manager at Dr. Jacob Energy Research. And I want to present you quickly the project Exquisite, focusing on standardized heat pump solutions for sustainable food production. This project is funded under the LIFE program and has just started about half a year ago. And it follows a little bit a different approach than the two previously presented projects, who are focusing very much on the implementation and testing of new technologies, whereas Exquisite focuses to support the rollout of industrial heat pumps and focusing on the technologies that are already available. Of course, as Matteo just said, industrial heat pumps are very viable and promising technology in different energy sectors and different industrial fields, such as chemical, pharmaceutical, pulp and paper. But we focus only in the project on the food and beverage sector. So we really want to analyze the local demands for individual processes. The project focuses on 4 industrial processes you can find in all different kinds of food and beverage subsector or sub-industry, which is pasteurization, hot water for cleaning and sanitation, refrigeration and cooling, and last processes is on evaporation, concentration, and drying. So these 4 processes are key throughout the whole food and beverage industry, and electrifying and decarbonizing these technologies, that's the goal of the project and how to support it. The first step is to analyze the industrial processes. So in the very moment, we are in the phase of data collection throughout all of Europe to analyze the real-life data and complement it by data from literature and from previous projects so that we can build on what is already there. Second is to develop standardized heat pump solutions. So we analyze the different processes, define their scales, their different designs, and then develop a standardized solution attached and focusing on this individual process then. Why we do this is to bring the knowledge of the standardized solutions to the heat pump manufacturers. So we have technical partners within the project. The project itself is rather small compared to some others. We are 9 partners from 6 different countries throughout all of Europe, and we cover the food and beverage sector as we have clusters within the project. And we also cover the technical heat pump sector with the European Heat Pump Association, but also 2 individual manufacturers. And we also want to bring these 2 sides together. So by the end of the project, we will establish a round table where we want to bring together the representatives from both fields to create a better understanding and a stronger exchange regarding the needs, but also the barriers you can find in both fields. And lastly, we want to raise awareness and provide guidance for companies. So for example, we will provide guidelines dedicated for decision makers in the food and beverage industry. So yeah, we can speak their language more or less, and sometimes go out from the technical perspective, but more into the entrepreneur perspective to really support the rollout of heat pump integrations. And on the next slide, I already addressed one question, but I think this rather fits also for the other two projects. If you ask, how can industrial heat pumps contribute not only to decarbonization, but also to European energy security? Or industrial heat pumps are a proven technology, and they are market available at the very moment. Of course, research, as we can see, is ongoing in the selection of heat source, but also in the pathway to reach up to higher temperatures for to expand the application field of heat pumps. At the very moment, it is a very uncertain time for fossil fuels. There are, different political challenges, also, wars ongoing in the world, and Europe is still highly dependent on fossil fuel imports. And if you don't, or if companies don't switch to use the local heat sources, which is basically renewable, then they are dependent. And this is not only a topic of decarbonization, but rather energy security. And the second point is, if companies focus on switching to synthetic fuels, to bioorganic fuels, as we see in the moment, this rollout for synthetic and bioorganic fuels and in general renewable fuels is lagging behind at the moment. So these are solutions we want to use in the future. But on a short scale, industrial heat pumps are the, from our perspective, the technology at the very moment, you can use, and which help facilitating the decarbonization in the European industry. Thank you very much. I don't know whether there are any questions, but I'm open for the discussion.
Yeah, thanks, Michael. Also to give an insight about the Exquisite Live project with a different approach and with no development on a heat pump directly, but more on how to integrate, what are the barriers and obstacles and how to overcome this. I think that's quite useful. And then the round of these three kind of projects, part of the 2COOL2WASTE cluster, it really shows the broad approach how to tackle this issue on the decarbonization of the industry with the different aspects and solutions which are now coming up. We will start the Q&A now in the next few seconds, but before that, there are already some questions in the chat, which are, I think, first of all, to our first speaker, again, asking about the intercooling loop. So more technical questions here, first of all, and then we will start again the Q&A as said. But with that, Vaishak, you can probably answer first of all this question, what kind of device you use here for the intercooling.
Yes. Okay, so for intercooling, it is pressurized water which we are passing through a heat exchanger. One side it is pressurized water, and the second side the refrigerant coming from the compressor discharge. And there was also another question whether the system is a closed loop, open loop, or a closed loop. Actually, this heat pump is a closed loop system, not an mechanical vapor recompression system. And there was, I think, one more question is related to geosyn. Which fluid was used to transfer heat from the source to heat pump? Actually, it was directly the steam which is coming from the geothermal well. That was the fluid, and that steam was at approximately at a pressure of around some saturated steam at a pressure of around some 4 bar.
All right. Thanks for this answering the question, which allows our audience to follow your technical developments. And there's another one for the SAS Heat project about the thermal energy storage, looking into different temperature levels, and the question how to select each kind of thermal energy storage, either on the high temperature side or on the low temperature side. Maybe you can give some more insight how to do this kind of methodology approach and how to select. Matteo.
Yes, thank you, Uli. Yeah, I mean, it's a very good question, and it depends on many factors. So basically, you have 3 types of thermal energy storage. You can have sensible, you can have latent, you can have a thermochemical. And from each one, you have to see the heat capacity of the material, mostly in the sensible one, or the enthalpy of phase change if you are using a latent heat, so a phase change material or a PCM. And in the thermochemical, you have to see the heat of the reaction, if it's endothermic or is exothermic. In the case of SUS heat, we are using latent heat, thermal energy storage. And apart from the technical consideration that I just mentioned, you also have to see sustainability. Are you using the recycled materials? If you are using, for example, sensible, if you are using stones, ceramics, or metal scraps. If you are using PCM, you have to see the compatibility and the safety of the material that is not corrosive for the mechanical structure of the tanks, and the same for the thermochemical, and of course the economics. You can have a very good material, but it's very expensive and make the system, let's say, non-feasible in the operation. But coming back to let's say, the temperatures, we chose latent heat thermal energy storage for SUS heat because it has a very good synergy with the Stirling heat pump, mainly because the Stirling cycle operates on the isotherms in the 2 temperature levels. So if you have a phase change material, which is mainly melting at 1 temperature or in a very small range temperature, if you are working at a fixed isotherm, you can melt the material more efficiently. If you had a bigger glide, well, at the beginning you can melt the material, but then if you go below the melting point, it's not very efficient. For the low temperature test, you have to see the temperature level of the waste heat. Normally in paper factories or food factories, you have water vectors that are mainly condensates from the process units, and the temperature can range between 40 to 90 degrees. So we choose a Crodatherm 74, which has a melting temperature of 75 degrees, 74. But in that low temperature side, there is a lot of, let's say, literature from all the residential applications in thermal energy storage. So let's say technologies are well developed and commercially available. It's more interesting to look at the high temperature one because between 180 and 250, there are not so many PCM phase change materials available at the commercial level. So we are working with a mixture of nitrates, which is similar to the solar salts, with a melting temperature around 220. And we chose this material because we need to have a melting temperature above the process temperature level, so the battery can actually give more heat to the process that is required. So there are, to wrap up the answer, many considerations that has to be accounted. But first, the temperature that you need for the process. I hope this clarifies the question. Yeah.
Yeah, you really dived in from different angles now into this question, and I hope that our colleagues here in this webinar now get a more clear picture of what kind of potential thermal energy storage with the different aspects can be used and how to integrate them and so on. So thanks for that, Matteo. I think this is really quite useful, and it's also part of this webinar really to have this possibility to explain in more depth the different aspects. And there's another question here about the heat exchangers, which are used for the polluted water flows, so tube and shell, spiral plate heat exchanger, what else for the different industries? So what kind of heat exchangers? And maybe that's something if you are doing implementations in your projects in the SAS heat and Geosync, where you probably can both answer these questions from your experience, from your colleagues which are doing the implementation. Maybe Matteo, just start, and Washik, you can follow up then here on this question.
Yeah, thank you for that question. I would say, like, normally the condensate from this process, it can have some solid particles. I'm not sure if we can classify them as polluted water flows. So, for example, I give an example in a dairy factory. You can have the condensate from the pasteurization process unit. So probably this water have some milk inside, but let's say the colloidal mixture of the milk with the water is not a problem for a heat exchanger. So you can have a water to water, because we have a secondary loop between the waste heat source and the stirring machine. We have this pressurized water loop. So in the source size, we have a water-to-water heat exchanger. It can be a plate heat exchanger if it's, I mean, if the solid particles are not so big. If it's polluted, I would recommend to have first a filtration step before actually to have the heat exchanger, so it's easier and more efficient. But if you have, for example, air source at 70 degrees, you will have a air to water heat exchanger. So these are, let's say, common applications for heat exchanger manufacturers.
All right, thanks. Washik, you can follow up maybe and give some insight from your experience in the project.
Yes. So for our project, all heat exchangers in our prototype are currently brazed plate heat exchangers. However, if the source is highly polluted, like large debris and all, then we need to shift to a shell and tube heat exchanger in that case. But currently, we are fabricating with a brazed plate heat exchanger.
All right, thanks for this second view and insights of your project, how you solve this kind of question. With that, we have another one here in the Q&A now, which is going to the Exquisite project. The question here is, how can be the solutions used from the project as a replication case to other kind of sectors in the future? Maybe you, Michael, you can somehow elaborate on this.
Yes, so we do focus a lot on the replication. Of course, what we see is also that every individual process in the food and beverage industry is very different from one another. So even pasteurization, whether it's for dairy or for orange juice or for already canned products. So we see that the processes are quite diverse. But we want to narrow our solutions down. So our solutions will be replicable also for different fields. And the total approach we follow is easy also to exploit and replicate in different sectors. So to analyze the actual needs, narrow it down to a standardized process, and then work on this. And once this standardized solutions is there, you can adapt it depending on the actual needs of the individual company. What we also want to develop, for example, within the project is a kind of a online tool that will help decision makers in the food industry to assess their process and their viability for a heat pump integration really at early stage and at a not in a very detailed technical way, but in a way that really makes it a step further in the total process of heat pump integration. So yes, the processes will be very replicable.
All right, thanks, Michael, for this answer. So are there any other questions from the audience? Because there's nothing else in the chat. I do not see anyone raising their hands. Maybe I have one short question to all of you three, because then we have to go on with the next panel. If you have to say 1-2 sentence, what is your wish that the technologies you are looking into now for the decarbonization industry, what is really needed to make the next step? Just one sentence, please. Vashik, you may start and then follow up by Matteo and Michael.
Yeah, for us, the biggest challenge is the development of compressor. So we don't have much available compressor for, especially for a closed loop application. So I would suggest that as the biggest challenge or biggest, opportunity in our field. And for this project, we are developing our own compressors. So that is the biggest challenge.
Okay, great, thanks. Nice research question. So Matteo?
Yeah, in our case, let's say the biggest challenge from a technical point of view were the sealings, the mechanical sealings for the heat pump. If we are going to higher temperatures, the sealings have to be stronger. And of course, we need to be successful with now the new experimental plant that we are building. So we are looking forward to do that. Yeah.
Great. And lastly, Michael?
Yes, for us, biggest challenge is rather on a social point, bringing people together, and also motivating people to do so. What we also see is, for example, that people kind of speak different languages. For example, we also have another project targeting a role of heat pumps in the chemical sector. And in the chemical sector, when you talk of high temperature, it's 600 degrees and higher, and not as for high temperature heat pumps like up to 200. So that's already what we see. So the language and the availability and exchange is for us biggest challenge.
All right. So yeah, thanks all of you three for this insight from the different projects. I hope with this discussion and with the answer Q&A, all participants of this webinar had some clue now what the projects are doing. If you are interested, of course, you can easily get connected again through the 2COOL2WASTE cluster along the different projects and have a closer look what they are doing, and probably hope to see you also in the next webinars here. And with that, I want to close panel 2 and hand over to the next panel to keep the time. And yeah, thanks again to you, three of you, and see you soon.
Thank you very much, Yuli, and to all speakers for this insightful discussion within panel 2. Let's move on to our third and last panel, energy systems working together, buildings, grids, and flexibility. While the first two panels focused on cooling and heat pumps at the technology level, this panel zooms out a little. We're going to be looking at how buildings, thermal systems, and energy networks can be better coordinated, not just made individually more efficient, but actually working together as one system. We have two guiding questions for this session. How can buildings, thermal systems, and energy networks work together to use energy at the right time? And how can multi-energy systems, MES, aid buildings, thermal systems, and energy networks to use energy at the right time? For this panel, we have two excellent speakers to help us explore these two questions. First, let me introduce Claudia Vannucchi. Claudia is a research fellow at IFER, the European Institute for Energy Research, a French-German research institute founded by EDF and KIT, based in Karlsruhe. She works within IFER's local multi-energy systems research group, which focuses on designing and optimizing local energy solutions and sector coupling. Claudia represents the Synergy Nets project today. It's a Horizon Europe project with 19 partners across 8 countries, coordinated by IFER. And Synergy Nets aims to demonstrate how multi-energy systems can decarbonize heating, cooling, power, and gas sectors with pilot sites in Milan, Ljubljana, and Paris. Welcome, Claudia. And alongside Claudia, we have Rongling Li with us. Rongling is an associate professor at the Technical University of Denmark in the Department of Civil and Mechanical Engineering, and she is the coordinator of the SEEDS project. SEEDS stand for Cost-Effective and Replicable RES Integrated Electrified Heating and Cooling Systems for Improved Energy Efficiency and Demand Response. The project focuses on data-driven optimization of heating and cooling systems in buildings to unlock demand-side flexibility, with pilot sites in Belgium, Denmark, and Slovenia. Welcome, Rongling. It's a pleasure to have you both with us today. Claudia, you will bring to this panel the multi-energy systems and sector coupling angle from the Synergy Nets project. And Rongling, you will bring deep expertise in data-driven building control and demand flexibility from SEEDS. So let's get started with the presentation of the two projects and the answers to both questions. I will now leave the floor to Claudia.
Okay, thanks a lot for the introduction. So yes, Claudia Vannucchi here today. I would start with why flexibility matters and how we can move from efficient assets to coordinated system. So basically what we see as Energy Nets is that the challenge is no longer producing energy. We have plenty of energy production. It is coordinating its use. So on one side, we have renewables, which are quite abundant in some EU countries, but they come with the issue of being extremely variable, as we all know. So for example, I can bring forward the case of Germany, in which we have an quite impressive amount of wind power in the north, so abundance of renewables, but the majority of the industries and so the electricity demand is located in the south. So that brings issues to the transmission system operators and generally the electricity grid to transport the electricity from the north to the south, and that comes with congestion issues and such, and need for heavy investment and reinforcement in the electricity grid. And on the other side, obviously, a high abundance of renewables can also come, as we've already seen this year on multiple occasions, with negative electricity prices, which are not extremely equipped well to deal with. On the other side, we have the building perspective. So the buildings are evolving. They're becoming more and more active energy players. So for example, they can have heat pumps, they can have PV, different types of storages, can be thermal, can be batteries, but generally they are changing from what transmission system operators, TSOs, and distribution system operators, DSOs, had planned their grid for. So we have a changing environment, and in this we see flexibility as a key value-creating asset to solve the challenges that we have at hand. So what is flexibility? First of all, so flexibility is basically the ability to change the energy consumption or production according to the electricity system needs. So that is a brief, definition. So for example, we could use a heat pump earlier or later by still keeping the same level of comfort for the consumers. We could use a heat storage to store heat for being used at a later date, or we could vary our CHP plant schedule to have a different electricity and thermal output. So basically, in this frame of mind, flexibility is what can allow the DSOs and TSOs to delay the expensive investment. We're talking millions every year for small DSOs and even billions for large TSOs in the electricity grid by only focusing on certain areas of the grid in which there are no flexible assets available. So yes, we've seen now that there is flexibility. It matters. Now the question is not anymore about why flexibility matters, or even if it exists. It is on who can coordinate it. And at Synergy Nets, we think that multi-energy system can be the link. So we can move to the next slide. So what is a multi-energy system? For those that don't know, it's quite simple. It's basically a system that can generate different kinds of energy. It can be electricity, heating, cooling, either all at the same time or only two of them, just generally can generate multiple types of energy. And it can also shift their consumption and production between the different assets according to either technical needs or market condition, which is extremely interesting when we talk about flexibility. So in Synergy Nets, we see that MES can turn flexibility into a coordinated system service. And what do we intend with coordinated? So basically, we can have many different energy assets, as we've seen in a multi-energy system, that are managed together through either a energy management system or through a market platform, rather than acting as an individual system. So in that frame of mind, I like the analogy with an orchestra. So basically a heat pump, a battery, a thermal storage, generally any energy technologies can be seen as individual musicians. So each one of them can contribute a bit of flexibility to the system, but on their own, the impact of the single heat pump or of the single EV charger, for example, it's quite limited. The multi-energy system acts as the conductor. So basically coordinate all of these different resources so they can work together and deliver a reliable service to the energy system so that the energy system operator can actually use this flexibility. So yes, that's why in Synergy Nets, we see multi-energy system as basically an enabler. So it is allowing the buildings or generally any energy demanding asset to collaborate with the electricity grid and, for example, the district heating and cooling networks. So all of the different energy networks. So the multi-energy system on its own, and we've seen that, we've actually developed that in Synergy Nets, can measure the available flexibility in the system. It can aggregate it across the different assets that it handles, and then it can optimize when these assets consume or produce energy to serve the electricity system operators. So in this energy transition, we see that before the main issue was adding renewables to the generation, and now with Synergy Nets, we think that the next challenge is the coordination on the grid. So flexibility is the resource that we have and we should use to delay the investment on the electricity grid, and multi-energy system is the mechanism that can help us use it at the right time, in the right place, and for the benefit of both consumers and the energy system. So we've actually demonstrated, because we're towards the end of the Synergy Nets project, that we can keep the same level of comfort for the building or generally end consumers of the district heating networks, while offering flexibility to the electricity grid. So yes, that would be my brief presentation, and we can get questions later if you want. Thank you.
Thank you very much, Claudia, for this very insightful presentation. I can't see any question for the moment in the chat, so maybe we can move to the next presentation by Wrangling and see if there are any questions in the meantime. Wrangling, please, you can go ahead.
Thank you very much. Here, I take the opportunity to give you a few examples from the SEEDS project. So I'm an associate professor at DTU. I'm also a cooperating agent for IEECP and X96, grid integrated control of buildings. So I have been involved in IEA project for a decade, working on energy flexibility of buildings. So could you please go to the next slide? I'll click. Yeah, okay. So for the SEEDS project, we have 6 pilot sites in 5 different countries. In Denmark, we have an office building. Belgium, we have 2 culture heritage neighborhood, and in Slovenia we have a 5 petrol station. Hungary have a residential building, Greece a dormitory, and we now is in the 3rd year, and it's in the year we actually already doing demonstration, implementing advanced control in buildings. I will give you 3 examples from 3 of the pilots, and could you please click the slide? Yes, great. So here, yeah. What we do is we use operational data and also design data to build models. And in the buildings, we have a management system. They collect data from real life operation. And then with the data, we build models. Then we apply using this model for optimization to optimize the control set point, for example. Then this control set point is sent back to the BM system to implement in the system to control. So what type of data we collect? We collect data from the HVAC system because this project is about heating and cooling, and so we collect detailed data from them. For example, in the Danish case, we have the new office building where we have 1,010 meters. We can get a resolution of 1 minute data. At the moment, we use every 6 minutes resolution data in the advanced control implementation. Next. Thank you. So I will show 3 examples. The first is the Belgian pilot site where they use the data-driven approach for optimum design and operation of a hybrid heat pump system. Next slide. So typically, when we design heat pump system, there's often a problem that is oversizing. So here in this project, our concept is that we know we can optimize the operation of a heat pump system. Then we should use that knowledge in order to optimize the sizing of the heat pump system in order to avoid oversizing and to make sure the heat pump is operating with a high performance, so high COP. So this is that approach, integrated design and operation optimization. In this way, we can also reduce the investment cost. And if you go to the next slide. This approach is tested in both Belgian pilot. This is example of one of the pilot where they use the ball field heat pump and also air source heat pump, and then with the PVT to use in the summer to collect the heat for hot water supply. And so this is a quite complex system because it's renewable integrated and multi-source of renewable. And for such a complex system, optimum design is a request. So this is a solution that is designed and applied in this case. So compared to a typical rule-based design, and the optimum design can reduce the cost up to 35%. And we can also test this approach in the future climate scenario. So with the climate warming, and we can study what this system will perform in the future. And this is also an approach that is considering in the Danish side, where we also look into the life cycle analysis of the building design and operation, taking consideration of future climate conditions. Okay, the next slide. Now I'm going to the Danish pilot. Here we are deploying gray box MPC to control the building heating and cooling system to provide the implicit demand flexibility. Implicit demand flexibility in this case is that we control this system based on the variable electricity price. From 2021, variable electricity price on hourly basis become available to all the end users. And so that's a quite common approach for adjust electricity demand from time to time according to the price level. And if you go to the next slide. So here, this is the approach we use to build the gray box model, and we take the data from the operational phase, that's the data collected in Data Hub, from the BMS provider, and we also take the drawings from the dialog system. We also use the weather data. So basically, based on this data, we can identify the parameter for the gray box model, and the detailed model for the building and the HVAC system is done in Daimler. And the next slide, I show the structure to deploy this gray box model. So you can see here in the center, there is MPC, that's model predictive control, and our building and HVAC system model is there as the model. And we use the optimizer to optimize the set point of the controller. So in order to do that, we need to access to many different type of data where we use the API. For example, the BMS system send us real-time measurements through API, and we also get the future electricity price through API, weather forecast, PV forecast, and we send back the control signal to the BMS through API. So in this case, we have our own database. With that, we also develop a user interface dashboard to show the performance of the MPC, and also to communicate with the building owners and the users in the office. So yes, this is the example of the Danish case. The next slide will be the example from the Slovenia case. Here, because we have 5 petrol stations from 5 locations, and here we have the DSO and the energy company involved in the project. The goal is actually to develop an aggregation platform to aggregate the distributed flexibility for explicit flexibility purpose. The next slide. So here is a sequence diagram and shows what is the process of deploying the flexibility. Basically, the DSO will request the flexibility, then our SEEDS platform, which is the aggregator platform, receive it and evaluate this flexibility request, send it to different buildings. Then the building will evaluate to see if I can offer flexibility. For example, if the DSO say I have big pressure at 1 o'clock in the afternoon for 1 hour, I need to have this peak demand reduction of 100 kilowatt hour, for example, then the buildings evaluate if they can reduce their electricity consumption at 1 o'clock for 1 hour, and how much they can reduce. So they send that back. They send that evaluation back to the DSO, and then evaluate. Say, okay, I take your offer, and please provide me what you have offered. Then the building will then activate these control devices. That is this MPC that we talked about, for example, for the Danish case. Then the controller will be activated at the building level in order to reduce the peak demand at 1 o'clock. Then this result will be finally evaluated by the DSO and the energy company. Then they will make a settlement to pay for this flexibility. So this is the process. The next slide will show you what is the digital infrastructure that enabling this process. Basically, on the pilot side, we have meters and controllers that control the system and the component. Then we collect data. The data is collected by the energy company who is the owner of this pilot site. Then the data is provided to the service developer who can utilize this data to develop a model and to provide optimization and send the optimized signal back to the SCADA, then back to the pilot site to implement the optimized control. So this is the digital infrastructure. It's the same for the Danish case where we have embedded the BMS system, and we also apply this control through cloud. I think that's all my slides for the SEEDS project with the 3 examples. Thank you.
Thank you very much, Ronglin, for your presentation. It was very insightful. I see that there are some questions in the chat, questions to Claudia first. We have a question from Joachim. What would be the approximate amount of flexibility that could be generated by an MES, a multi-energy system, in your project?
Yes, I can give you, let's say, an off-the-book example. I can give you a ballpark number because we're still waiting for the final publishing of the deliverable. But for example, for the Italian demo, which is basically a big, large multi-energy system, we're talking 2 air-to-water heat pumps, 1 geothermal source heat pump, gas boiler, electric boilers, gas engines and such, and they're supplying a large part of the Eastern district heating network in Milan and a large part of, obviously, electricity onto the grid. We're talking something around 10 gigawatt hour of flexibility for a system that provides 10 gigawatt hour thermal of district heating network demand. So that is just to give you a rough number, which obviously we didn't test the flexibility provision for the whole year. So we tested on specific, let's say, representative weeks of the year, and then extrapolated this number. So it doesn't mean that for a system that provides 100 gigawatt hour thermal to district heating, it's for sure that we can get 10 gigawatt hour electric of flexibility for the electricity grid, but that is a ballpark number for you.
All clear. Thank you very much for your response. And we also have another question to you, Claudia, from Atul. He's asking, from your experience, what are the key technological and market barriers to scaling automated demand response solutions in buildings? And what measures are needed to accelerate the adoption of smart controls, IoT devices, and building energy management systems?
Yes, so honestly, at least for us, the main issue has been in the Slovenian demo, for example, less with the, let's say, technology and market, more with actually signing customers that were willing to participate in getting, let's say, their temperature inside their houses change slightly, obviously. So we conducted all of the tests in a way that we wouldn't impact, like that was the goal, the ultimate goal, no, of the project, to provide flexibility without changing the comfort. So we managed to do that, but that was the main issue that we found, rather than technological or market barriers. So literally convincing the customers that yes, it makes sense to do this, that they can get a return, and that their comfort level won't change.
All clear. Thanks a lot for your answer, Claudia. We have still a bit more minutes for the Q&A, so the audience, please do not hesitate to... Yes, I see a hand raised here. Pal, you can go ahead. Do you have a question that you would like to share with us?
I think the microphone is not working.
If you have any issue with your microphone, maybe you can drop the question in the chat and we can read it to you. In the meantime, there was a question from Joachim to Wrangling. What would be the role of smartification and data for engineering solutions?
Thank you. So the role of smartification and data is essential. If we don't have a smart controller available, if we don't have data available, we cannot develop engineering solutions. So for SATES, the goal is to replace fossil fuel-based heating and cooling solutions with the renewable energy-based solutions. With the renewable energy, as we can see from also the previous presentation, we need to, it's not reliable, and we need to have a control for make sure our demand is followed the generation of renewable energy. So that make all the things complex, and it really require engineering solution. For example, when we have a renewable integrated heat pump solution, then we have geothermal, we have a PV, then system become very complex. The design of the system is a complex engineering process. Then the operation is also, it's not a task that can be done manually. For example, when a facility manager need to manage such complex system, they need to have a tool that can help them. So this is where the engineering part come in. As engineers, we need to design and provide such automated tool for the facility managers to be able to utilize renewable energy-based complex heating and cooling solutions in an optimum way. For doing that, digitalization and smartification of the system and data collection is really essential.
Thank you so much, Rongling, for this very detailed question. I hope that it clarified the question. Pal, maybe are you able to ask your question? If your mic doesn't work, maybe in the chat. I don't see any question for the moment. Feel free to ask any question you may have in the chat. Maybe I would have myself a question to Claudia. Rongling presented the pilot in detail for her project seeds. Maybe you could give us, Claudia, some more concrete examples from your pilots in Milan, Ljubljana, and Paris, and also in comparison to seeds pilot, maybe what worked well and what has been harder than expected.
Yes, of course. So the two pilots in Milan and Ljubljana, they are third generation district heating, so quite older compared to other district heating network. The Paris one is a fifth generation district heating network, so basically top notch, the latest thing that you can get. It's an ambient loop. So what we've seen that was a bit tricky, I mean, obviously much easier once you have a multi-energy system that is both the owner and the operator of the network. So for example, it was a bit trickier for the Paris demo site, in which we had in the consortium the operator of the network, but not the owner of the buildings. So it was really hard for us to gather data from the owner of the building because of privacy issue and such. While, for example, for the Milan or the Ljubljana, it was still, obviously, it's always a challenge to gather data, but much easier. While for the Paris one, yes, that was tricky, and it took quite a long time to gather this data. What else? We can see that it changes a lot from one demo to the other. So, for example, the Slovenian demo was a lot more fossil fuel based compared to the Paris one, which was basically 100% renewables, or the Milan, which was a good 50-50. So that was also a bit harder, as our goal was obviously to decarbonize as much as possible while offering flexibility and maintaining the same level of comfort. So that was also longer than expected in the planning. So we were supposed to transition from a coal fired CHP to a gas fired CHP, and that also generated some delays. So generally, yeah, with any, I think, especially public funded project, it always takes a little longer than you had originally planned.
Many thanks. It's very clear. Thanks a lot for your response, Claudia. And also, Pal wrote his question in the chat. It's about the large water heat pumps. It's also for you, Claudia. And the question is, do you consider large wastewater sourced heat pumps that you can connect? And Pal adds that the heat source can be mapped and planified to optimize projects.
Not in Synergy Nets, but we at IFER have. So we've been doing that for France, for example, because we are a French-German institute. So that is definitely something that we're looking into. So finding out the potential and how we can valorize the heat from wastewater treatment plants with heat pumps. So that is something that we definitely have considered, not in Synergy Nets yet.
All clear. Thank you.
Thank you.
And we also have a question from Hélène. How do you look at multi-energy system and flexibility with the transition away from fossil fuel movement? How do your project in the next 20 years, what would be the tail of needed fossil fuels in MES?
That is a tough question. But yes, no, generally, the goal of Synergy Nets was obviously to present also a future pathway to decarbonize the energy system. So all of our demonstrator made effort and strides into decarbonizing their energy supply. So that is something that we have considered from the very first day. I believe we should have some projections on the future of the energy system. I sadly do not have the numbers in mind at the moment, but I believe I can get your email and look into it. It was a deliverable on which I didn't work, so I don't have the number right now on the top of my head, but to have projections for future energy scenarios in Europe as well. So I should be able to come with an answer for you.
Great. Many thanks, Claudia. Rongling, is there anything that you would like to add also related to the several questions that have been asked in reaction to what Claudia said as well?
I think many countries has a decarbonization pathway and heavily rely on energy supply. When we do the LCA analysis, looking to the future, if we consider if the energy supply of electricity and district heating is decarbonized according to the plan, then we will meet some target, and that is really important. However, at the same time, there is a lot of pressure in electrify the system on the grid. So nowadays, we, for example, in Denmark, the heating is really predominantly by district heating, and this means almost all the buildings in cities connected to district heating. On average, 65% of buildings are connected to district heating. If district heating going to be electrified, that would means a very large additional electricity demand from to the electricity grid, and how to make sure we have enough renewable energy generation, we have big enough transportation capacity from the grid, then what is the cost associated to that is a big question. At the moment, we are all looking to what is the cost-effective way of electrification of both of the district heating, and so in this sense, the flexibility play a big role, because when we reduce peak demand, we can actually make sure reduce the capacity demand for the grid. So this flexibility definitely plays a role in the future energy system, especially the decarbonization and the electrification of district heating.
Thank you so much for these insights, and thank you so much, both of you, Claudia and Rongling, for such a thoughtful discussion on how buildings, networks, and multi-energy systems can come together to use energy more intelligently. It has been really insightful. Thanks a lot. And that brings us to the end of our final panel for today. And let's move on quickly to the wrap-up. So as we come to the end of today's session, I'd like to take a moment to thank all of our speakers and moderators across the three panels, Katia, Uli, Carla for panel 1, Veshak, Matteo, and Michael for panel 2, and Rongling and Claudia for our final panel. If I try to draw a common thread across the three discussions that we have today, I think it's this. We've moved from individual efficiency gains towards smarter, coordinated systems, whether that's generating cooling from waste heat, recovering value from low temperature heat through heat pumps, or getting buildings and grids work together on flexibility. The direction is the same. It's not just about making one component more efficient, it's about making the whole system smarter. And as a reminder, as I said at the introduction of this webinar, 16 European-funded projects make up the 2COOL2WASTE cluster, all working on different pieces of this same puzzle. And I would encourage you to follow up with the individual project websites and the speakers if you'd like to dig deeper into any of the topics that we have covered today. As I said at the beginning as well, this session was recorded and will be made available afterwards on the different websites of our cluster initiative. Thank you once again so much for your engagement today, for your answers in the Mentimeter, for the questions in the chat, and for being such an active audience today. This wraps up our 2COOL2WASTE cluster webinar. We are right on time. Thank you again and have a great rest of the day.
Thank you very much.
Thank you. Have a nice day.
Thank you. Bye-bye.
Thank you. Have a nice day. Bye-bye.
Thank you. Bye.
Thank you. Have a nice day.
Bye-bye. Thanks.
Thank you. Bye.